All right, we're going with this. Cool. All of that and half the class still missing. All right, we're going to get going. So, let's see. So hopefully you turned in your homework. Questions on the homework. If there's anything you weren't sure about, let's talk about it today so you have time to think about it, work on it, do more practice problems, and then ask more questions on Wednesday. And I'll give these back to you on Wednesday with some comments, but you know, this stuff is fair game for the midterm, so I want to make sure you're clear on the proofs involving numbers and properties of numbers that were in that homework. So any questions from that assignment? Doing another example with the number proofs. Yeah. Anybody else use primarily indirect proofs for the n odd even, then on is odd even? So some of those work well with direct, some of them work well with indirect. So let's do an example of each. Let's prove that if n and m are even numbers, then n times m is also an even number. And this would be a little tricky with an indirect, but a direct proof is going to work well. All right, so break it down into propositions. If proposition, then another proposition. And we're trying to prove if this, then that. In other words, this implies that. So, you know, maybe this is the proposition P, this is the proposition Q. We'd like to prove P implies Q. How do we do that? We take P as being true, and we try to show that we can get to Q being true. So this is why we state hypotheses, right? So let's start off by stating the hypotheses. First hypothesis, n is an even integer. I didn't say integer up here, but I would normally. So n is an even integer. Okay, reason, always got to be present hypothesis. I'll go ahead and write the second one. M is an even integer. That's also a hypothesis. So what's a possible third step I could write here? Definition of even. So we can write n as 2 times an integer. There exists some element k in z that's an integer, k, such that n is equal to 2 times k. That's got to be true because k was an even. I mean, n was an even. And yeah, we can do the same thing here, and good, you're still using separate variables. There is a j in z such that m equals 2 times j. That's also the definition of even. All right, so what do we do next? This is the magic step. Multiply. What should we multiply? N times m equals 2j times 2k. Perfect. And I'll go ahead and expand that out. And I'll factor. And that's substitution and algebra. and some commutivity thrown in there too. I'll subsume the commutivity under algebra for now. And so we've written n times m equals 2 times something, and what can we conclude from that, right? You know, we can write 2jk as an integer, properties of integers. Now we've shown absolutely that n times m is 2 times an integer, which means n times n is even. And that's definition of even. And that's what we were trying to show. N times m is even. So there's our QED. Alright, so questions on this. This is an example of a direct. We'll do an indirect next. Alright, let's try an indirect proof. About how to end an indirect. Oh, okay. So let's see. We just showed that if n and m are even, n times m is even. Prove if n times m is odd, then n is odd or m is odd. Alright, so again, so we have a proposition here and we have a proposition here. If this is P and Q, we're trying to show if P, then Q. So step one, let's assume the hypothesis. So n times m is odd, that's the hypothesis. And then let's negate the conclusion. So we assume negation of n is odd or m is odd. That's the negation of the conclusion. Let's go ahead and throw De Morgan at this because it's just screaming for De Morgan when you have a conjunction or disjunction with a not in front of it that really says, you know, put De Morgan here and you'll simplify this. So we distribute this by saying, you know, n is even and m is even. And that's De Morgan applied to 2. And now we can, you know, assuming that we've done this in the previous part of the problem, perhaps, right? We know that if n and m are even, then n times m is even. So now I'm going to say n times m is even. And the reason, see above or prior page or something, right? If you do this on a test, don't just refer back to something we did 5 days ago in class, right? If you haven't proved it on your paper, you're going to have to prove it. But we'll assume that, you know, this was what we just did. So we know that since n and m are both even, n times m is even, right? And now we have a contradiction because proposition 1 says n times m is odd. So 1 and 4 contradict. each other. Okay, so this is where some people are inclined to stop, but finding a contradiction doesn't prove what we're trying to do unless we tell the person why this contradiction proves that. Why does it prove it? Because this statement must be false. Right? That's the thing that we assumed, and it led to a contradiction. So this statement is false. Therefore, n is odd, or m is odd. And that's what you were trying to show, so that's where you say QED. And those two are really the essence of all these proofs. Proofs about divisibility, proofs about evens and odds, all those kinds of things. They're basically look like this, right? Write down everything that you know, use definitions if they're available, and then for an indirect proof, negate the conclusion, and then go from there to a contradiction. For a direct proof, just keep using what you've already stated is true and try to get down to a statement of the thing that you're trying to show. Again, a really big part of this is the way in which you present it. Right? You can have all the steps and, you know, just say 2k times 2j is such and such, and have it not be a valid proof at all. Right? Because you didn't start off by saying n is an even integer because that's a hypothesis and so on. Or, you know, there is an integer k such that n equals 2k. If you just start multiplying 2k by 2j without telling me anything about k and j, it's like, you know, what does that have to do? Where did it come from? What does it mean? You're trying to make, you know, kind of a legal argument here. So a lot of this is about the presentation, and even if you don't get the sort of magic step, you know, of factor out of 2, right, you get a lot of credit for how you put the proof together, right? If anything, that's where I want to see most of the effort. But I'll try to give you problems that you know, don't grossly hide the path to the conclusion. All right, other questions? There's a second textbook that's posted on Canvas, and that one does a lot more with the number stuff. I don't know if it does even odd proofs, but it gets into some of the stuff. Yeah, midterm discussion is coming up next. Any other homework questions? Well, feel free to ask them now or come by office hours. Well, let me talk about the midterm, and if someone comes up with more homework questions after that, we can talk more about homework too. Let me talk a little about the midterm. So your midterm is Friday, and it starts at 12:30, and it runs 80 minutes. I don't think you need 80 minutes, but I don't see the point in doing, you know, a 55-minute exam and lecturing for 25 minutes after you've already done, you know, a 222 exam and a 215 exam and maybe a physics exam. So I'm going to give you the full 80 minutes. Okay. So it starts at 12:30, and it finishes at 1:50. All right. It will appear on Canvas like a homework assignment. Okay, but it'll open at 12:30 Friday, and when you look at the entry on Canvas, you'll see a PDF file, and that'll have all of your questions in it. You have two options for turning in your answers. Either you can write your answers neatly, just like you do on your homework, and take nice legible pictures or scans of them, turn those into a PDF and upload. Okay, so it looks just like a glorified homework assignment. That's one solution, perfectly acceptable. If you prefer to type, you can go into your favorite word processor, type up your answers, and then turn that into a PDF and upload that. Okay, either way, the upload to Canvas has to be a PDF. And please, organize it in a way so I don't have to struggle to try to figure out what you were trying to do. So put things in order, make sure that, the question that you're answering is clear, put the question number in the margin. If you're writing it up by hand and it's not clear that the last thing on the page is your answer, circle your answer, and so on and so forth, right? So just, something reasonable so I can follow it. Pretend that, I'm handing you this exam in the classroom and you're handing me back your answers, right? But we're doing it by PDFs instead of on paper, basically. So it's not going to be a Canvas quiz. It's not going to look like the stuff we did last quarter. It's just going to look like a homework assignment. So at 12:30, the assignment will open. You'll see a PDF that will have all of the questions in it. Write out the answers, upload those as a single PDF file. So two comments I made in an announcement yesterday. One, office hours tomorrow start 15 minutes late because I have a CS meeting that goes till 9 o'clock. So I won't be in my office until 9 o'clock tomorrow. Two, what I just told you about the midterm, I put in an announcement. But also emphasize that the exam will not lock you out at 150, right? You can upload it late, but there's going to be a point penalty, and it's severe. It's 5 points per minute. So make absolutely sure you upload your exam answers before 150. If you turn it in 5 minutes late, that's going to be a 25-point deduction, okay? So it's really not like a grace period, like I need an extra 10 minutes, and Nick's being nice by leaving the exam open, right? It's simply a way to avoid having people send me emails and things like that with late submissions. So Canvas will let you turn it in whenever, but the deadline is 150, okay? Unless you've made arrangements for extended testing time, turn it in. Technically 20 minutes late would be a 0. But don't play with those numbers, Yeah, and your grade won't go negative. But yeah, just make sure you turn it in by 150. The other thing is, I want you to be on Zoom, right, during the exam, so that, if I made a typo in a question, if I ask you to do something that's impossible, something like that, I can put a message in chat, right, and say, hey, question 5, ignore because it's impossible, right? If you're not in Zoom, I have no way to tell you that, right? So at least hop into Zoom. You can mute your microphone. If I need to tell you something, I'll put it in the chat message. I should have chat disabled for everybody else, so anything that comes up in chat should be coming from me. And I will give you a reminder right before, like about 1:45, and say, you've got 5 minutes left. And at that point, I would say, stop what you're doing and submit your PDF. And make sure you know ahead of time how to turn your work into a PDF, right? Don't try to figure it out Friday during the test. Practice ahead of time whatever you're going to use, OpenOffice, Google Docs, Microsoft Word, print a PDF from Mousepad, whatever you're going to do, practice ahead of time. Make absolutely sure you know how to make your PDF that you can upload. Because if it's, 149 and you're trying to make your PDF and that option's not available in the way you thought it was, and you do something else and you got to reboot your machine and all that, and you don't get it uploaded till 2 o'clock, right? You've lost 50 points. So figure out the mechanics early, right? And you can submit more than once, right? If you're feeling good about your answers at 1:30, you can submit those and keep working on them, and go like that. And I'll grade whatever the last submission is that you make. So you can keep adding to your PDF and resubmitting, and that's totally fine. And then if something happens at 1:45, a tree falls down and your power goes out, well, you've still got your latest upload. So basic management, crisis management, that kind of thing. All right. The other thing is, at the top of the exam, you will see an honor statement, and you're required to read and agree to that honor statement as part of the exam. And at the top of your answers, you're going to type the word or write the word honor statement, followed by your signature or your typed full name to indicate agreement. And the honor statement basically says you're going to do your own work on the exam. You're not going to consult other sources. You're not going to ask anybody for help except me. You're not going to offer help to anybody. You're not going to use any online resources other than your notes and your textbook. Okay? So pretty basic stuff. It's an honor system. We're not doing lockdown browsers and all that kind of stuff. I hope we never have to go to that, because those things are really intrusive and yucky. So everybody's on their honor to stick to this. Other than that, the exam should be pretty straightforward. So what will you see on the exam? It looks like 7 questions, which doesn't tell you anything, because 7 questions could be short or long, but everybody wants to know how many questions there are. But you will see questions from any of the following areas: set theory, functions, propositions, propositional logic, membership tables, Venn diagrams, summation notation, rules of logic, laws of inference, fallacies, tautologies, pretty much anything that we've done up through the homework that you just turned in, right? So no multiple choice. It's all problems you're going to write out. There's some proofs. There's some, write down this kind of thing, stuff like that. I believe it should be doable in 80 minutes. I believe it should be doable in less than 80 minutes. So don't take the 80 minutes to mean that it's going to be a really long exam that takes longer than class. I'm just giving you the 80 minutes in case you want to work more leisurely or need the extra time. But there'll definitely be some proofs on there. There could be some number theory stuff. There could be some set theory stuff. Best suggestion: go back and look at the homeworks. Look at the things that we've done in class, the problems we've worked out, the things that we've talked about. There's extra problem sets in the textbook, right? There's a whole slew of odd-numbered questions that have answers in the back. There's supplementary questions at the end of each chapter, and there's worked-out exercises throughout each chapter. And all of that stuff is kind of, along the lines of what you're likely to see on the exam. So hopefully no surprises. And yeah, probably no multiple choice. All right, so questions about that? Is there a way for you to re-upload Friday's lecture with a transcript despite there being no recorded sound? Only if I went back and repeated everything that I said and recorded it, because there's just no record of it. The microphone was on, right, because you could hear me during the lecture, but the recording software apparently noticed that the microphone wasn't there before, and it switched input sources, and I think it switched to one that was muted. So, technical glitch. But most of what we did Friday, you know, was and what we talked about. Well, let me see what we did Friday. So what did we do Friday? So we spent a while going over the homework questions 1 and 6, right? So the question about fallacies and the question about divisibility. And then we talked about the fundamental theorem of arithmetic, which was, you know, about unique factorization into primes, and ways of testing primality, doing trial division, looking at how many primes there are, the prime number theorem, and then some open questions, Mersenne primes and Goldbach's conjecture. And let's see. And none of that is on the midterm. I mean, fallacies could be, because that was preliminary stuff. But none of the new stuff, none of the number theory stuff that we did on Friday should be on the exam. So the stuff about primality and factoring into primes and stuff like that. So yeah, that's a bummer that we missed it, but it shouldn't affect you Friday. Yeah, modular arithmetic is fair game. And the main thing about modular arithmetic is finding the remainder when you divide A by B, right? So A is congruent to B mod M means that A equals M times, you know, some integer plus B. In other words, B is the remainder when you divide A by M. Right? In other words, it's just the percent operator. All right, so here's the thing. This is part of my waking up at 4:30 in the morning, which is why I'm a little brain dead. So I'm going to defer the rest of our number theory discussion until later. Okay, so I had said we were going to talk about applications and crypto systems and RSA, and I'd still like to get through those, and we'll at least get back to some of that eventually. But I want to switch gears at this point, and I want to start talking more about proofs, and in particular I want to talk about mathematical induction. And the reason is that, you know, we basically missed Friday because of our midterm, and then we missed Monday because it's a holiday. So we have 2 days this week and then no more lecture for another week. And if I spend today and Wednesday finishing up number theory, we won't get to induction for another week and a half. And I want to kind of sync it up with what we're doing with binary trees in 222. So we're going to switch gears and go back into propositional logic now and talk about mathematical induction. And this is really the core of CSE215. Okay, this is the primary reason that this is a generally a prerequisite for 222. And this is good stuff. This is life-altering material. So, all right. So mathematical induction. Let me start with an example, kind of a real-world example, right? So there's an expression: a journey of 1,000 miles begins with a single step. Right? So what does that mean? You're standing, on the road, and you're trying to get to a place 1,000 miles down the road. Okay? There's two things in that proverb. Journey of 1,000 miles begins with a single step. The first thing, which is really sort of the main punchline, I think, when people say that, is you've got to take that first step. If you don't make that first step, you won't be able to make the second step or the third step or the step that got you to mile 1,000. So you've got to begin, right? But hidden in that proverb is also the implication that once you've made that first step, you can repeat the process. You can make, another first step, which would be your second step, and another first step after that, which would be your third, and you can keep doing this one step at a time until you've traveled 1,000 miles. Okay, this is the essence of mathematical induction. So more formally, here's what we're going to be doing, but keep that proverb in mind, and we'll come back to it from time to time. So let P of n be a family of propositions. And I'm going to assume that n is an integer, and just for now, I'm going to assume that n is greater than or equal to 1. Now I could do this for any family of integers, really. I could have n bigger than or equal to 0, I could do n bigger than or equal to 15. I could do n is a prime number bigger than 11, right? But for most cases, we'll just assume n is an integer bigger than or equal to 1. And P of n is a family of propositions. It's a set of propositions. And for any value of n, I get a different proposition. So, e.g., P of 1 is a proposition. P of 2 is also a proposition. P of 3 is a proposition. And so on. For example, let P of n be the proposition. I don't know. P of n could be the proposition, it's possible to eat n eggs. Okay? It's not very mathematical, it doesn't have to be, it's just a collection of propositions. P of 1 is a proposition, it is possible to eat 1 egg. Let's say in an hour. P of 5 is the proposition, it's possible to eat 5 eggs in an hour. Alright, it's a family of propositions. As long as n is bigger than or equal to 1, P of n is a proposition. P of 50 is the proposition it's possible to eat 50 eggs in an hour. Alright, everybody clear? So when we talk about mathematical induction, we're always talking about a collection of propositions. Usually it's going to be P of n, but n is just a placeholder. I could have said P of k is a family where k is an integer bigger than or equal to 1. Okay, our goal is to prove, say, P of n for all n bigger than or equal to 1. In other words, we would like to prove that every proposition in this collection of propositions is true. P of 1, P of 2, P of 10, P of a million, P of a trillion. And in general, to prove that P of n is true for all n, well, if we prove these one at a time, we need an infinite number of proofs, because there's an infinite number of integers bigger than 1. But there's a shortcut we can take sometimes. So our goal is to prove P of n is true for all n bigger than or equal to 1. We can do this if we show two things. Not an infinite number of things, we only have to show two things. Alright, first thing we have to show, prove that P of 1 is true. So up here, prove it's possible to eat one egg in an hour. The second thing we have to show, prove that for any n bigger than or equal to 1, P of n implies P of n plus 1. In other words, prove that if P of n is true, then P of n plus 1 is also true. If we can prove both of these things, then we can claim that P of n is true for all n. And you should note that this is very different from that. This is a really, really strong statement. This says every P of n is true. This is just saying if P of n is true for some given n, then it's also true for n plus 1. Okay, so is it possible to eat n eggs for any integer n bigger than 1? Probably not. We can't use this proof. We can show that P of 1 is true. It's possible to eat one egg in an hour. But there's probably some n that we can eat n eggs in an hour, but we just cannot eat n plus 1 eggs. Right? It's going to be really hard to show that this is always true. And in fact, it's probably not. There's some limit. Maybe I can eat 50 eggs in an hour, but not 51. Alright, but let's look at an example of a family of propositions where we can prove this. Let's test this, yeah. Nobody has cited the reference that I'm making either. Let P of n be the proposition that the sum from I equals 1 to n of 1 is equal to n. In other words, if you go to your calculator and you do 1 plus 1 plus 1 n times, you'll end up with n. Now we believe this is true, but have you ever proven this? I mean, we know 1 plus 1 will give us 2 and 1 plus 1 plus 1 will give us 3. But how do we know that if we do 1 plus 1 a million times, we'll actually end up with a million? Oh, backyard chickens, awesome. Yeah, I am so getting chickens when I get a house. So can we prove this? Can we prove that the sum of n ones is equal to n? And it takes a bit of work. I mean, it's so obvious we don't really think about how would we prove this. But how would you prove this? I mean, we can prove it for a particular n. I can show if I add 5 ones, I'll get 5. I can do that by just adding 1 to itself 5 times. But how do we know this works for all n bigger than or equal to 1? And we can do it using mathematical induction. So mathematical induction says we have to prove two things. Alright, so we've got our proposition. Step 1, we want to show that P of 1 is true. Okay, so P of 1 says the sum from I equals 1 to 1 of 1 is equal to 1. Well, sum from I equals 1 to 1 of 1 is just 1, and 1 is equal to 1, so I'm just going to say that's true. That's just a calculation, and we can see that that side's equal to that side. Alright, step 2 says we have to prove that if P of n is true, then P of n plus 1 is true. Where n is some integer bigger than or equal to 1. I'm not going to prove that the sum from I equals 1 to n of 1 is equal to n. I'm going to assume that the sum from I equals 1 to n of 1 is equal to n, and I'm going to prove P of n plus 1. So this is like a little side proof now. So let's prove P of n gives us P of n plus 1. Alright, so step 1, let's assume the hypothesis. Step 2, let's state the hypothesis. Sum from I equals 1 to n of 1 is equal to n. That's the definition of P of n. Without illustrating why I'm going to do this, I'm going to do the following. And the whole trick to induction proofs is figuring out what this next step is going to be. And it might be right here, it might be later down, but again, there's always this point where you've got to sort of see how to twist things around. So I'm going to write something down that's absolutely true, but not necessarily clear why we're writing it. And that's going to be this. I'm going to break my summation into two pieces and say if I take the sum from 1 to n plus 1, that's the same as the sum from 1 to n, and the sum from n plus 1 to n plus 1. And that's a property of summations that we did, I think, in week 2. And we can split our sums up like that. And I'm going to write the sum from I equals 1 to n of 1 plus, well, what's the sum from I equals n plus 1 to n plus 1 of 1? That's just 1, right? Because this says add up 1, 1. And the sum from I equals 1 to n of 1 is equal to what? That's equal to n. That's algebra and substitution from step 2. Yes. Well, what did we just show? Right? We wrote this down by breaking our summation up, and then we showed that that right side's equal to this plus 1, and then we substituted this summation, which we know is equal to n, and we showed this sum to n plus 1 is equal to n plus 1. We've just proven this proposition. Well, that proposition has another name. This is also P of n plus 1. Right? P of n is the proposition that if we add the sum up to n, it will get n. So if we do P of n plus 1, that's the proposition that if we take the sum to n plus 1, we get n plus 1. Well, we just showed that. So P of n plus 1 is true. Therefore, P of n implies P of n plus 1. Right? So we started with P of n. We did a direct proof that P of n plus 1 is true. Well, guess what? We've just proven that P of n implies P of n plus 1. That's true. I'll go back to step 3 in a sec. So now we've proven the 2 steps that we need for mathematical induction. So we can say, therefore, P of n is true for all n bigger than or equal to 1, and the reason is mathematical induction. And that's the end of our proof. All right, let me go back to the mechanics of step 3, and then we'll go over the big picture again. Step 3, I wrote down this sum from 1 to n plus 1 as a sum from 1 to n and a sum from n plus 1 to n plus 1. That's a particular case of this thing that we saw week 2. Which is that we can take a summation like this. And split it into 2 pieces if we like. Or let me do a less abstract example. For example, the sum from 1 to 10 is the same as the sum from 1 to 5 plus the sum from 6 to 10. Or the sum from 1 to 9 plus the sum from 10 to 10, which is what we did there. Cool. All right, so lots of things going on here. There's a lot of machinery involved in this. Our goal is to prove P of n for all n in some class, like for all n bigger than or equal to 1. And we do this by proving 2 different things. First proving that P of 1 is true, and then proving that P of n gets us P of n plus 1. And then we put those together and say, therefore, by the decree of mathematical induction, P of n is true for all n bigger than or equal to 1. Mathematical induction is that decree. It's that big stick we can hit problems with and say, hey, we proved this and this, therefore we know that this is true. All right, so let's keep going through examples. Kind of laggy for me. You mean the Zoom session or the concepts conceptualizing? Or the video? The Zoom? Yeah, mileage may vary with Zoom, I'm afraid. Alright, well, I'm not lagging here, so the video shouldn't have lags in it. So if it gets really bad, going back to the video should help. But Zoom seems to like get fast and slow during any given Zoom session, so maybe it'll improve. Alright. Let me give you another hand-wavy example, and then we'll go back to a more mathematical one. Hand-wavy example, climbing a ladder. Suppose you have a ladder from here to the moon, and you want to know, can you climb this ladder all the way to the moon? Right? You would need to know 2 things. One, you need to know that if you are standing on a certain point on the ladder, a certain rung, you can rise 1 rung higher. In other words, you can always go up one step. If there's some point where, you know, you're standing on one rung, but there's no way you can reach the next rung, it's too far away, or the air's too thin and you pass out or something, right? Then you can't climb to the moon. But assuming that from any rung you can go up just one more rung, right? If that's true everywhere, you can climb all the way to the moon. Okay, that's all there is to mathematical induction. But there's another property that needs to be true, which is you have to be able to get to the first rung of the ladder. If the ladder is sitting on top of the space station and you're not on the space station, you can't get to that first rung, right? Then you can't climb the ladder to the moon. So you got to be able to get to that first rung. That's, you know, saying P of 1 is true, and you've got to know that if you can get to a particular rung, you can get to the next rung. Okay, so let me do a more formal statement of mathematical induction. It's the following theorem. So again, let P of n be a family of propositions where n is bigger than or equal to 1. It's an integer. Everything in sight is an integer for now. I'm not recording the video on Zoom, actually. Zoom is strictly just streaming what you see on this desktop, and I'm recording with other software. And I switched my camera, and so my CPU is not sounding like a 747 and ready to take off, so I think my CPU load is low. But network speed, who knows around here. Alright, so let P of n be a family of propositions where n is bigger than or equal to 1. Here's what mathematical induction says. It's a theorem. It says if you're given P of 1 and you're given P of n implies P of n plus 1 for all n bigger than or equal to 1, then we can conclude P of n for all n bigger than or equal to 1. That's it. That's everything we're going to be doing for the next week or two. This is one theorem. Given P of 1 and given that Pn implies Pn plus 1, we can conclude Pn for all n. Alright, this is called the basis step, and this is called the inductive step. Alright, questions so far? Alright, more examples. Let P of n be the proposition. Okay. Yeah, it could be. Let P of n be the proposition that the sum of the first n integers, 1 plus 2 plus 3 plus ... up through n, is equal to n times n plus 1 over 2. And we'll do this for n bigger than or equal to 1. All right, well, a good first question to think about, do we believe this proposition? Do we actually think this is true? So what do you think? Is this true? Is it true for any values of n? What value of n do you think it's not true for? Well, let's pick an n. Let's pick n equals 3. Infinity is not an integer, actually. Let's not get too harsh on it, though. Let's say n equals 3. So P of 3 is the proposition sum from I equals 1 to 3 of I is equal to 3 times 3 plus 1 divided by 2. Well, what's the sum from I equals 1 to 3 of I? What's this side equal to? Sure. It says take a 1, take a 2, take a 3, add them together. That's equal to 6. What is 3 times 3 plus 1 divided by 2 equal to? Also, 3 times 4 is 12 over 2 is 6. So for n equals 3, this seems to be true. For n equals 1, P of 1 is the proposition that the sum from I equals 1 to 1 of I is equal to 1 times 1 plus 1 over 2. Well, the sum from I equals 1 to 1 of I is just 1, and 1 times 2 over 2 is also 1. So P of 1 looks like it's true. P of 3 looks like it's true. P of 2 basically says 1 plus 2 is equal to 2 times 3 over 2. Well, 1 plus 2 is 3, 2 times 3 is 6 over 2 is 3. So P of 2 looks like it's true also. So it kind of looks like, at least from the first 3 values of n, like P of n is plausible. So let's prove this. So to prove it with mathematical induction, we have to do 2 things. We have to prove a basis step, and we have to prove an inductive step. Alright, so here's our proof. Step 1, this is the basis step. P of 1 says sum from I equals 1 to 1 of 1 equals 1 times 1 plus 1 over 2. And so, you know, do this in your calculator, this will be 1. Do this in your calculator, this will be 1 times 2 over 2, which is 1. This is true. Now, if this is something more complex than this, then you need to, you know, actually show what this is equal to and do your work and take derivatives and integrals and cosines and whatever else, right? And then do the same thing here and show they're equal. But, you know, most of the time, this is something that you can look at and you can say, yeah, this is true. And, you know, maybe I would say something like, you know, this is equal to 1 and this is equal to 1. Just to say I did some work, right? But this usually is kind of a slam dunk. Okay? The bigger challenge is proving the inductive step. Prove P of n implies P of n plus 1, where n is some bigger than or equal to one integer. Okay, so how do we prove this? We're trying to prove an if-then statement. What's a good first step? Yeah, this is the famous formula for triangle numbers, and I think it was Pascal, but I think I get that wrong usually. But yeah, famous mathematician. The teacher was apparently punishing the class and told them to calculate the sum of numbers from 1 to 100, and he like came up a minute later with the answer 5050. And he basically intuited this formula. Yeah, that's a cool story. You kind of had a homework question like that did something similar, right? If you want to add the numbers from 1 to 100, if you do it in the right order, it's 1 plus 100, 2 plus 99, 3 plus 98, 4 plus 97, and each of those adds up to 101, which is that part. And you do that n over 2 times. But assuming we're not as smart as Pascal or whoever that was, let's do this with induction. So what's a good first step of a proof? Now forget everything about mathematical induction, right? Forget everything we've done today, and let's just go back a couple of weeks and say, hey, here's a proposition. P of n says, you know, this thing is true, and I want to prove P of n implies P of n plus 1. So yeah, good first step, hypothesis. P of n is true. What's almost always a second step after we state a hypothesis? It's almost the only other thing we can do at this point. Definition, exactly, right? We've said P of n is true. Well, there's really nothing else we can do at this point, but we could, you know, write down what P of n is. So let's do that. Well, since P of n is true, the sum from I equals 1 to n of I is equal to n times n plus 1 over 2. Why? Because that's the definition of P of n, and we just stated that P of n was true. And now we got some formulas and some Greek symbols, and we're rocking and rolling now. We can do stuff with this. There's enough here to manipulate. Now this is where we want to do our ignore section. So I'm going to mark a clearly delineated area. I am lagging now, which says ignore. Anything I put in here, you won't lose points for. I won't consider this to be part of the proof. On the other hand, anything that you want to be part of the proof, you have to put over here, not in the ignore area. All right, what am I going to put over here? I'm trying to show P of n plus 1. I'm going to go blah, 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 and today's Tuesday, blah, and chickens lay eggs, blah, 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 and therefore P of n plus 1, right? Well, if I know what P of n plus 1 says, I got a better chance of figuring out how to get there. So usually what I'm going to do over here is write down P of n plus 1 says, and I'm just going to write down the definition. So P of n would say the sum from I equals 1 to n plus 1 of I is equal to n plus 1 times n plus 2 divided by 2. You gotta have the squiggly line ignore section. If I were to write this over here, my proof just failed. Right? Because I haven't shown that this is true, and if I put it down here as step 3, I'm stating something that's false. Well, I can prove anything I want after that, right? It's not a valid proof. But I'm putting it over here just to give me an eye where I'm heading, right? You got to know what you're after sometimes if you want to hope to find it. So I know this so far, right? This is what I'm trying to get to. And so now you put on your puzzle solving hat and you say, how in the world could I get from this equality to that equality? And there's probably no obvious way to do that. But you try to find something that might move you in that direction. A little bit like a sequence. We've got n times n plus 1 over 2. We've got n plus 1 times n plus 2 over 2. Well, there's an over 2 on the bottom, but the top part doesn't look very similar. But look at the left-hand side. Look at this, and look at that. Those are pretty close to each other. What would I have to do to change this expression into that expression? What do I have to do to this to make it equal to that? I have to add something, not quite 1. I have to add one more term. Add an n. And it's actually an n plus 1, but you've got the idea now. So I'm going to do the following. I'm going to say step 3, and we're going to do a bunch of algebra here. I'm going to say the sum from I equals 1 to n plus 1 of I, because that's what I'm after, right? And I can't say it's equal to that. Bad proof. But I can do anything that's provably true. I'm going to say the sum from I equals 1 to n plus 1 of I is equal to the sum from I equals 1 to n of I plus n plus 1. Right? This comes out of properties of summation. Because this is just adding, the terms up to n, and this is the n plus first term. Everybody okay with this? Ask now if you're not sure why this is true. And it has nothing to do with mathematical induction or anything we've done. This is just a property of summations. Cool. Alright, well this sets us up for some great magic. Okay, so I took this sum from 1 to n plus 1 and I split it into two sums. Sum from 1 to n, and then basically, the sum from n plus 1 to n plus 1. Because what is this thing? The sum from 1 to n plus 1 is 1 plus 2 plus 3 plus n minus 1 plus n plus n plus 1. Okay, that's what we mean by the sum from I equals 1 to n plus 1. Well, this thing, this is just the sum from I equals 1 to n. But what we're doing with mathematical induction is we're avoiding these dot dot dots. We could do all this by saying dot dot dot, but dot dot dot's not like a propositional calculus thing. All right. So we've just done something benign looking, but really, really powerful. We said the sum from 1 to n plus 1 is the sum from 1 to n plus the number n plus 1. Properties of summation. Well, I'm going to use what we've already done, which was we showed that the sum from I equals 1 to n of I was n times n plus 1 over 2. That's step 2. I'm going to substitute that for this summation. So this is substitution of what we had in step 2. And the substitution was putting this thing in place of that thing. Well, now it's all algebra. Multiply this out. N squared plus n over 2 plus n plus 1 equals n squared plus n over 2 plus 2 times n plus 1 over 2. So they're both over a common denominator, so we can combine those. N squared plus n plus 2n plus 2 divided by 2 equals n squared plus 3n plus 2 divided by 2. And then I'm going to factor the top. Into n plus 1 times n plus 2. And why did I get excited when I started doing that? Because in my ignore section I knew I was trying to get to showing that this sum's equal to that expression. And guess what? That's what we just did. We just showed that the sum from I equals 1 to n plus 1 of I is equal to n plus 1 times n plus 2 over 2. And that equality is p of n plus 1. So the reason for all of this was algebra. Well, what did we just do? We assumed p of n, we did some stuff, and we showed p of n plus 1 is true. Therefore, p of n implies p of n plus 1. So we have proven what we were trying to show in step 2. We proved what we were trying to show in step 1. We've proven the base case and the inductive step. And so now we can say p of n is true for all n bigger than or equal to 1. The reason is mathematical induction. And that's what we were trying to show. The algebra step definitely is part of the proof. If you put it in the ignore section and then just say this is equal to that, you're leaving the reader to figure out what you had to figure out to do this. So anything that's not going to be completely clear to somebody who's not very good with this stuff has to go as part of the proof. So yeah, definitely put it in your main section. The ignore section is really just, to tell me where I'm trying to get to. Like, oh, I'd like to have a sum up to n plus 1, and I'd like to have, n plus 1 times n plus 2. To help you while you're fiddling around and factoring and combining terms and things like that, to get a feeling for, oh, this feels like it might be going in the right direction, Or if you start getting, like weird things over here that look nothing like this, maybe I should try a different direction. These take a lot of practice, right? But really, once you get through enough of them, you start to realize that most of the problems you see look like something you've already done. Okay? But again, this is the classic physics experience. Right? It looks like, every question that you have on homework has nothing to do with any other question. But after you've done enough of them, you start to realize, like, oh, it's the same set of, 15 or 50 or however many. It's the same set of this finite set of possible approaches to solving this problem. And that's kind of how this stuff works. Yeah, this will definitely be your next homework. But I'm not going to give you your next homework until Wednesday, because it's not going to be due until next Wednesday, since Monday's off. All right. So there's the mechanics. There's being able to agree faithfully that this is a valid proof. Okay, that's the mechanics. And then there's the insight, which was, oh, I should write this sum like this, add n plus 1 to this, and combine and eventually get to there. And that's the thing that comes with practice and looking at lots of examples and working through lots of examples. And then there's the higher level aspect, which is this machinery we call mathematical induction, which is this idea that if we prove P1 and we prove Pn implies n plus 1, then we can get P of n for all n. So I would take a look at the book. I think it's chapter 4, it could be chapter 5. Take a look at the book. Go through the examples that they have in there. And Wednesday we will just start going through lots of examples of this. And we'll play with some examples that are very mathematical in nature, and we'll play with some that are very non-mathematical in nature, including things like putting tiles down on floors or throwing pies at people, or enumerating the number of different colors that horses come in. And we'll just run the gamut of different examples. And this will be something that will come back to the rest of the course, and it's something that we'll come back to throughout CSE215, right? So it's going to be kind of foundational, and that means we're going to have a lot of chances to look at it and to approach it from different things, and it probably is not going to totally sink in the first few times, right? So if you're working with this and you're trying to do a problem and it's not making sense, that's okay. That's part of the process of learning it. Right? The fact that you're going through that and you're hitting a wall and you're not sure how to get past it, that means you are learning it, right? And it's not always a fun process, but it definitely gets you somewhere good. Oh yeah, it may be at the end of chapter 3, maybe like 3.8, something like that. It's in the book. Check the contents. All right, cool. We are out of time. That was a fast class, I think, because I was messing with my tech in the beginning. Have a good one. I will see you next time.